In this lecture, we're going to take the same next step that we did when we were talking about areas. Once we learned how to find the area under a function, under the graph of a function, the next thing we did was we learned how to find the area between two functions. And the way we did that, if I can borrow my diagram over here for just a minute, we found the area under the larger function, the upper one, and then we subtracted out the area under the lower one. Concept you learned originally all the way back in your high school geometry classes. Well, in this lecture, we're going to do the same thing with volumes. Right? Let's say we want to find the volume of the solid generated by rotating this area between the curves around the x-axis or around the y-axis. The process will be exactly the same. Okay, well, the way we do that, again, is going to rely on this exact same geometry concept. We have the circular regions generated by rotating the upper curve. And what we want to do is subtract out the circular regions generated by rotating the lower curve, right? So if we use, we're going to kind of rely on our disk method here. If we use the disk method to find the area under the the volume generated by revolving the upper curve, and then subtract from that the volume generated by the lower curve, we'll get what we're looking for, right? So what's the volume going to be then? According to our disk method, the volume generated by rotating the upper curve is going to be it's going to be pi times the integral from a to b of f of x squared dx. And the volume generated by rotating the lower curve, this is the part we want to subtract out, it's going to be minus the integral from a to b. Whoops, don't forget the pi out in front. Integral from a to b of g of x squared dx. Now that's a little bit of a mess. We don't usually write it that way. Usually we combine these two to get two integrals together. So I'm going to factor out the pi, and then I'm going to combine the two integrals together into one. We're going to get pi times the integral from a to b of f of x squared minus g of x squared dx. And there's my formula. Right, now, this method has a name. It's called the washer method. Right, and the name comes from it. If you look at the diagram over here, these sections here that we get, right, they look an awful lot like washers. Right, so hence the name the washer method. So I've got our formula for the washer method here written out a little more neatly. And one thing I do want to make sure you're aware of before we move on to looking at some examples. You remember back when we talked about the disk method, we saw that it didn't matter if the function was positive or negative. Since the disk method says integrate the square of the function, and the square of the function obviously is always positive, we didn't have to be concerned about getting negative values creeping into our sum, which we did see happen back when we were talking about areas. Unfortunately, we do have to be concerned about that here with the washer method. Right? If the upper function here is f and the lower function is g, in this region, f squared minus g squared is going to be positive. But over here, in this section, for example, where they've flipped, right? They've reversed. Over here, f squared minus g squared is going to be less than or equal to 0. It's going to be negative. So if we just kind of blindly went ahead and used this formula going from 0 all the way over here to b, yeah, we'd run into trouble because we would get some negative areas added into that sum, and we'd end up with the wrong result. So What do we do here? Well, we do the exact same thing we did when we were doing this with the area between two curves. You have to take into consideration, you always have to consider when you're first setting these things up, do the two graphs cross somewhere in the region that I'm interested in? And if they do, well, you do the exact same thing. You do the exact same thing that we did when we we're doing this with areas. You just have to split the integral up. So instead of doing the integral from 0 to b to find the area between those 2 points, I would have to do the integral from 0 to a of g squared minus f squared plus the integral from a to b of f squared minus g squared. Right? And don't forget I almost forget the pi's. Don't forget to put that pi out in front. Okay, so really nothing radically new here, right? It's just, this is a little different from what we saw with the disk method.